However, if you now, so that, well, that leads to the detection, and you know, if you just want offline a 5 sigma detection, then you know that is the way to go. But then, as a next step, you'll want to measure the parameters of the black holes, and then you know, not just mass spins, but also sky position and so on. And then you need to do a little bit, or that is then the next step. And in that step, you're faced with a 15-dimensional parameter space, because again, now you are interested in the extrinsic parameters like the sky position, orientation of the orbital plane, distance, and so on. So you want to take those parameters along. But actually, if you even if you were just interested in a very accurate measurement of the masses and the spin, you would still have to take all these other parameters along, because they will be correlated. All of the parameters will be correlated with each other. And so a 15-dimensional parameter space, and then you can think, well, again, maybe going to lay out a template bank, but now imagine that, you know, in each of 15 dimensions, you even if you only lay out 10 points, you end up with 10 to the power 15 templates and 10 to the power 15 likelihood calculations, and that becomes unmanageable. So you have to do something else. And so that is going to be most of my talk. And so we will do this through Bayesian inference. In the Bayesian framework, what you do is you use the available data to do two things, often at the same time. You can construct probability distributions for parameters associated with hypotheses, and an hypothesis can be, well, an hypothesis is always, or almost always in our case, an hypothesis means that you assume there's a signal in the data, and not only that, it follows a certain waveform family. So these could be, in the case of binary black holes, in-spiral merger ring-down waveforms with or without precessing spins. Or in the case of binary neutron stars, you might get away with in-spiral only waveforms. But also the hypothesis could be that GR is violated, and then your waveforms will allow for some GR violation, and so on. So that is what hypotheses mean, and these hypotheses indeed come with parameters, of course, just in the ordinary case it's just masses and spins and what have you. But also you can do model selection. If you want to know is GR right or is GR wrong, then you can consider those two hypotheses and try to rank them on the basis of the data and see which one comes up top. And in the Bayesian framework, you are actually forced to make explicit all of the extraneous assumptions you are making, and that is a very nice feature as well. I'm going to just here establish some notation. So you have a bunch of propositions which would, for instance, correspond to hypotheses, A, B, C, and so on. Then you can define conjunctions, say that A and B are both true, or disjunction, A or B are true, or both. Negation means that A is false, and then of course implication from A follows B. Now it is useful to think of these operations in terms of set theory. So you have a so-called universe which contains subsets, of course, and so for instance then the conjunction A and B gives you the intersection of the set A and the set B, or disjunction A or B gives you the union of the two sets. Then negation gives you the complement of your set within the universe. So if the white blob here is your set, then the negation of if that is A, then the negation of A is all the red. So all of the universe that is not A. And then we're doing statistics, so we assign probabilities to these statements or sets. And so if A is a subset of B, then it had better be the case that the probability of A is no larger than the probability of B. Also, if you have two sets that are disjoint, their intersection is 0, then the probability of A or B is equal to the sum of the probabilities, and the universe itself has probability 1. So for instance, the probability of some set plus the probability of the negation of it is equal to 1. A and the negation of A are, of course, disjoint sets. So that is just notation, of course. And so now, some more notation then. We're going to define a conditional probability. P here is to be read as the probability of A given that B is true. And we define this to be the probability that A and B are both true divided by the probability of B. Okay? Well, this leads to the so-called product rule. So the probability that A and B are both true, that is a new notation I'm inventing here, but that is what it is then the probability of A given B times the probability of B, that you can read off just from this definition of conditional probability. Now, something that is actually somewhat annoying is that it is customary to also write explicitly, indicate that there is other stuff going on in the background. There's background information that we will have. In the case of gravitational wave detection, that background information includes the fact that the data came out of an interferometer, and that interferometer might be glitchy or it might be very stable, and so on and so forth. And that is what this I denotes. So probability of A, we're going to start writing as probability of A given whatever background information we have. And similarly for other statements. And this I is now going to be dragged along all over the place. And of course I could in principle just leave it out and that would simplify things, but once you start looking at actual gravitational wave literature, you'll see that I appearing all over the place anyway, so you might as well get used to it, I guess. But all the essential formulas are unaffected. So, for instance, the product rule is now the probability that A and B are both true, given whatever background information we have, is the probability of A given B and whatever background information, times the probability of B by itself, given whatever background information we have. Now, this expression here is symmetric in A and B, so in the right-hand side I might as well write the probability of B given A times the probability of A. And so setting those two equal to each other, I immediately get what is called Bayes' theorem. You will probably have seen this before in some form or the other. It says that the probability of A given B is equal to the probability of B given A times the probability of A by itself divided by the probability of B. That's Bayes' theorem. And that's now going to be a recurring theme in this very Bayesian talk, I guess. This is convention or notation, whatever you want to call it, marginalization. Suppose that you have some sets A and B, then the statement A and B and the statement A and not B are clearly disjoint. They are incompatible with each other, so as sets they are disjoint. And the union of those sets is A. So therefore, the probability of A is just the sum of the probability of A and B being true plus the probability of A and not B being true. Now, this is a trivial statement, but now let's generalize that. Consider a set or a bunch of sets B sub k such that they are all disjoint, all of their intersections for each pair is 0, and they are exhaustive in the sense that the union of all of them is the universe. So that in particular the probability, the sum of probabilities for all of the B sub k's is equal to 1. Then you can just write the probability of A is the sum of the probabilities of A and BK being true. And this is called the marginalization rule. Now in this discrete setting, this may seem like, well, what is this really useful for? It becomes more important when you go over to statements about continuous variables. So for instance, consider a proposition that says some continuous variable x has the value alpha. Well, since typically such a statement will be a set of measure 0, you cannot really assign a probability to that, or it has probability 0. So what we do instead is we assign probabilities to a parameter being within some finite interval. And then it is useful to introduce what is called a probability density function. And if you want the probability for this variable to be between some x1 and x2 value, you integrate that probability density function between x1 and x2. And then exhaustiveness is written as, well, if I integrate my probability density function over the whole allowed range of my variable x, I have 1, I get 1. And that is just a statement that the probability density function is normalized. I'm sure this is, stuff you all know, but well, repetition won't harm. And then this is then what marginalization looks like for a continuous variable. If you have initially a probability density function for A and some variable x, where A can either be some statement or it can itself be a variable, and you're not interested in the variable x, well, you just integrate it out and you get the probability for A by itself. So that is all introduction. So now we go to how to do parameter estimation. So in parameter estimation, suppose that some experiment has been performed or some observation, in our case, has been made, and we have data D collected, and we want to measure parameters theta, so that could be again the masses and the spins of some binary black hole merger, or in the case of binary neutron stars, I'll talk a little bit later about how neutron stars in a binary tidally deform each other, and that will leave an imprint on the waveform and can be parameterized and so on and so forth. Now, consider some model, and again, a model in our case will almost always mean a waveform family. So you consider a waveform family that allows you to calculate the probability of getting some data D, assuming you know the parameters theta. That if you can do that, then that is called the generative model. So for a generative model, you can calculate the probability of getting data of a certain form, given a hypothesis and parameters to go with them. Let me be concrete straight away. So what would this probability for getting certain data given a hypothesis, so a waveform model, and a bunch of parameters, can be more than one, and whatever background information we have, what would that expression be? Well, at least in the context of this talk, I'm first of all going to, first of all, what is the data? Well, the data is noise plus a waveform with some parameter values. That is what the data is going to be. Now, how would you calculate this probability distribution for the data, given that you have a waveform family and parameters? Well, what you've seen many times now is that if you assume stationary Gaussian noise, then you have a probability distribution for noise realizations. And it looks it is proportional just to e to the power minus a half inner product of noise with itself, where this inner product for any two functions a and b, it was just defined by Alicia before lunch, is this power spectral density weighted inner product. So you take the conjugate of the Fourier transform of A, and then B of F weighted by the noise power spectral density, and you integrate over frequency. That is what this inner product is. If we know that the data consists of noise and there is a signal in there, because the search pipelines have already indicated that with 5 sigma or whatever, then I know that this is true. So I can write the noise as data minus that signal that's in there. And that gives me an expression for this guy here, because then the probability of getting certain data, given that I know there is some waveform with parameters theta in there, that's going to be proportional to e to the minus a half. And for n, I now just substitute d minus h, and I'm done, right? So d minus h of theta, inner product with itself. And so I have a generative hypothesis, because the definition of generative hypothesis is I can, based on a hypothesis and parameter values, I can calculate the probability I will get data of some form. Here it is. And then there's a normalization factor in front here that I'm not writing. So now, so this we can calculate, all right? Because well, I've just indicated how to do so. In fact, next time I'll write a little bigger. But I think you got it probably. But actually, what we want is not this. What we want is the probability that the parameters take on the probability that the parameters take on certain values, given the data and hypothesis. But of course, you can convert one into the other using basis theorem. So what we want is the probability of getting certain parameter values given the data and hypothesis, and that is equal to the likelihood, the probability of getting data given a hypothesis and parameters. This is what we can calculate, it is right here, times the probability of the parameters given the hypothesis, divided by the probability of the data given the hypothesis with no information or assumptions about parameters. Now, what is this factor here? The probability that the parameters take on certain values given the hypothesis. It is the prior. It is our, in a sense, our knowledge of the parameters before the experiment or observation, or what we assume simply about the parameters. So, for instance, if you're looking for extragalactic sources of gravitational waves, then you can assume that they are isotropic. They can come from any directions. So you'll have an isotropic prior on your sky position. If, on the other hand, you're looking for sources in our galaxy, then it will be one that is adapted to the fact that our galaxy is an elliptical galaxy, and most stars are near a certain plane, and so on. And then there's the evidence here, that is this denominator that doesn't depend on the parameters. And so when we're doing parameter estimation, for now we can ignore it. We will come back to it, however. And so what I get in the end then is the probability of getting certain parameters giving data and a hypothesis is the product of this likelihood, which again we know how to calculate, times a prior probability density, which is something we have to make up in a sense, or information can come from a previous measurement. I is, like I said, I is whatever background information we have. And so the data came out of an interferometer. One is located in Livingston, the other is located in Louisiana, and so on. So I'm hiding everything that I don't want to make explicit in I. It's an annoying convention, but again, this is what you will see in research papers throughout. So that's parameter estimation then. So it's, again, this is what I had on the previous slide. The posterior density functions for parameters are proportional to the likelihood times the prior. And so conclusions are drawn based on information available from the experiment, before the experiment, that is the prior here, and then also from the experimental data themselves. And then, of course, you can extend that to more parameters. I implicitly already did this by putting a vector sign on theta here. This is trivial. And then finally, if you have obtained posterior density distributions for a whole bunch of parameters at the same time, but if you're only interested in the distribution of one of those parameters, you can just integrate out all of the others, and that is the marginalization that I was talking about earlier. So here you're only interested in the parameter theta 1, and you integrate out therefore parameters theta 2 through theta n. And then there's a whole bunch of other things that are probably also reasonably well known to you. How do you calculate the mean of a one-dimensional distribution in this example? Well, you just take your variable and you integrate it against its posterior density function. Similarly, you can define a variance, and then you can define, in case of more variables, you can also define a mean for any one of the variables, and then you can define covariance matrices and so on, but that here in this context will not be so important. And then confidence intervals. So if you want the 90% confidence interval based on a posterior density function for some parameter, so the gamma is the 0.9, that's the 90%, you just find the smallest interval such that the integral of the posterior density function equals that confidence. And you can have multidimensional confidence intervals and so on. That's not so interesting now. Let me go on now. So now I go on to, this was parameter estimation, now we go on to hypothesis testing. So here we want to compare different hypotheses, like I said, the hypothesis that the waveform came from a binary black hole and is consistent with general relativity, or there could be some violation of GR. Or you could have the hypothesis that you have you had a binary neutron star merger where the equation of state of the neutron stars were very stiff, or alternatively the hypothesis that the equation of state was very soft, leading to a lot of deformation in the neutron stars, or little deformation, and so on. So if we want to compare different hypotheses based on the data, then again we use Bayes' theorem. So first of all, the probability that some hypothesis is true given the data and nothing else, so there's no parameters here or anything, is equal to the probability of getting data given the hypothesis times the probability of the hypothesis, the prior probability for the hypothesis, divided by the probability to get certain data, assuming essentially nothing else. Now, again, we want to rank hypotheses or compare two hypotheses based on the data, which is the more plausible one. And that you do by just taking the ratio of the probability of x given the data and the probability of y given the data. And now if you plug in Bayes' theorem here, you see that this becomes just this ratio here, probability of data given x times probability of x, probability of data given y times probability of y. And what has dropped out is the probability of the data given essentially nothing else, which is very hard to obtain. I mean, I wouldn't know how to calculate that or what to put down really, but it drops out anyway because it's not dependent on what hypothesis you consider. And so once again, well, we have a ratio of prior odds here. You have to specify a ratio of priors for hypothesis X versus hypothesis Y. And now you have a ratio of evidences here, which is also called a Bayes factor. Now, what we calculated before were these likelihoods here, these likelihood function, probability of the data, given a hypothesis, and whatever parameters come with it. But here there are no parameters, so we need to find a way to compute what are called these evidences here, probability of D given X. So, well, we return to what we had earlier. What we had earlier was this here, probability of getting parameter values given data and hypothesis is the likelihood times the prior divided by this evidence here. And this evidence this time is actually what we are interested in, is probability of the data given some hypothesis. So I throw this to the left-hand side, and this is what I get. And what I want to calculate now is this guy here, the evidence. But that is easy, because I can just marginalize over all parameters on both sides. So I integrate out all of the parameters in both sides. And what happens in the left-hand side? Well, let's focus on the left-hand side here. This integral here, you see that the evidence, of course, is independent of parameters, so I throw it out of the integral. What is left is an integral over the posterior density function for all the parameters and over the full parameter ranges. But that's equal to 1, because this posterior density function has to be normalized. So the left-hand side is simply the evidence, what we want to know. So now we have an expression to calculate the evidence. It is just this right-hand side here. So what is the evidence? The evidence is the likelihood times the posterior integrated over all the parameters, and that's it. So, and then we can do our hypothesis ranking. So we return to our odds ratios, so which can now be written as a ratio of evidences. We now know how to calculate those evidences, and again, a ratio of prior odds. And then an issue is, well, a hypothesis can have an arbitrary number of free parameters, right? And now you can have different models where you're trying to describe the same thing, but suppose that one of your models has more parameters than the other model. Then you would think that the model that has more parameters will automatically come out on top, simply because the more free parameters you introduce, the better you will be able to fit. Like von Neumann said, give me enough parameters and I'll fit an elephant, give me even more, I'll fit its tail. So do we not run the danger that if one hypothesis somehow has more parameters associated with it, that it automatically gets preferred in this Bayesian game? And the answer is no, but let me illustrate why not. So for simplicity, let's compare just two generative hypotheses where the hypothesis X has no free parameters whatsoever, and hypothesis Y has one free parameter, lambda. And so now the question is, since it has a free parameter, is it the case that Y will automatically be favored over X? That is, will the odds ratio O for X versus Y, will that automatically be smaller than 1 favoring Y? So now, well, that means we have to calculate these evidences here. The evidence for X is whatever it is. You have a generative hypothesis, so you can compute it. In the case of Y, you take the formula I showed earlier, but for one free parameter. So you integrate the likelihood against the prior. For this simple illustration, I'm going to assume a flat prior. So I'm going to assume that my prior is constant in some range from lambda min to lambda max. Well, that means that the prior on lambda has to take this form here. It is a constant equal to 1 over lambda max minus lambda min, because if I integrate over this range here, I need to get 1, of course. So this is what my prior looks like. Now we need to worry about the likelihood here, which will go into the evidence for Y. So prior we've taken to be a flat prior. So what are we going to take for the likelihood? Well, since in gravitational wave physics we will be encountering likelihoods in some Gaussian form all of the time, well, let's just choose a Gaussian likelihood. It is only an example that I'm giving here, right? So assume that for this parameter lambda, you have this Gaussian likelihood function. Then we can calculate the evidence for y. We just integrate the likelihood against the prior and we'll be done. And so the prior is a constant, and then the likelihood is here. We all know how to take the integral of a Gaussian, so this integral can be done analytically, and this is the result. By the way, sigma here is of course the variance appearing in this Gaussian, and then you have the prior range at the bottom here. Okay, so now this is what we get. The probability, or rather the evidence for y is up to some constant is equal to this ratio here. So the variance of the likelihood divided by the range of the prior. So now we know the prior odds. The prior odds for hypothesis x versus hypothesis y takes this form here. You have a ratio of priors, which you could set to 1 if you don't know, if beforehand you claim no knowledge of x versus y. So this ratio of priors you could set to 1. These are just constants. And now you have the ratio of prior range divided by the variance here that appears in the likelihood for lambda. Now, this factor here basically compares best fits, and usually it will be smaller than 1, because again, a hypothesis that has an extra free parameter will probably fit the data better. However, if this parameter lambda is not needed, if it is a redundant parameter, then this factor here will penalize you to such an extent that the wrong hypothesis will not come out on top after all. If you're making a good measurement, then this variance here, which is essentially your measurement accuracy, will be small compared to the prior range, so this factor will be very large. And this factor will overcome this ratio here in case this parameter lambda is not necessary after all. And so Bayesian statistics has an inbuilt version of Occam's razor. Occam said it is vain to do with more what can be done with fewer, or at least I'm paraphrasing Occam. So that's all very nice, but now comes the big problem, and now actually comes the more exciting stuff. So what I said before is probably these are things that you already knew in some form or other, and well, nothing shocking or surprising there. But now we need to calculate all of the things that we said we would. So, for instance, suppose that you want to do parameter estimation. And this is the expression you are interested in. You want a posterior density function for parameters theta given data and a hypothesis, which involves a likelihood, and then a prior distribution, and then this evidence here. Now, often, like I said, the parameter space has high dimensionality. Just in the case of binary black holes, you have a 15-dimensional parameter space. And what are the 15 dimensions, by the way? They are comprised of two masses, then two spin vectors, but each of those spin vectors at some reference time is a 3 vector, so that's 2 times a 3 vector. And then you have 2 angles for the sky position, and then you have 2 angles for the orientation of the orbital plane with respect to the line of sight, again at some reference time. And then you have the distance, and then you have the time of arrival, and then the phase of the wave at arrival. If you count that up, then those are the 15 parameters I keep talking about. Now, suppose that you want to, get your posterior probability distribution for the parameters over this 15-dimensional parameter space, then you have the problem that I hinted at earlier. You would have to calculate the likelihood at, well, something you could do in principle is calculate the likelihood on a grid in this 15-dimensional space. But then you're back at that problem where, like I said, if you even only want 10 points in each of the 15 dimensions, you have 10 to the 15 points in parameter space where you need to evaluate the likelihood. And the likelihood here it's still written here. It takes this form with this inner product here, and that inner product is an integral, which needs to be done numerically, because the power spectral density, for instance, is often not a very well-behaved or nice-looking function. It may be, on the whole, well-behaved, but in any case, you would have to numerically do an integral 10 to the power 15 times, And even then, you would only be covering, each dimension of your parameter space by 10 points. That's not going to give you a good picture of what the posterior density function looks like. And similarly, if you want to calculate the evidence integral, and again, to obtain the evidence for a hypothesis, what you need to do is integrate likelihood times prior over all of parameter space. And that's a similar problem. If you want good resolution for that integral, then 10 notches in each of 15 dimensions is really not going to do it. Now, there is a saving grace, and what saves you basically is that usually it is the case that the likelihood function is strongly peaked somewhere in parameter space. And almost everywhere else, it is essentially 0 and therefore irrelevant, and you don't even want to know what it is there. It'll be 10 to the minus 55 or whatever. Let it be that then, that's almost 0 anyway. But the trick will then be to find where in parameter space the likelihood is peaking. That is then the next question. And that a priori that is a problem that sounds just as bad as the problem I just sketched. And now there's several ways of doing that, but since I only have so much time, I'll illustrate the one that is called nested sapling. Let me first introduce some notation. So here again is the evidence is of course the integral of likelihood against prior, and let me just simplify notation by introducing this. L of theta is the likelihood, pi of theta is the prior. Okay, and now we need a way to do these integrals here. Now nested sampling is a neat trick. Essentially what it is to reduce this 15 or higher dimensional integral for the evidence integral, for instance, to reduce that to a one-dimensional integral. Now, surely that would be a miracle. How can that be? How can you do that? And the answer is, well, you can't, but you can do so approximately. And if the approximation is good enough, then you're done. So now, how are we going to reduce to a one-dimensional integral? Well, I'm going to introduce first something called a single scalar called the prior mass. Now, what is the prior mass? Well, suppose here is my parameter space, or some box, because in each of the parameter directions you will have some range. Of course, this thing doesn't go on infinitely in practice. But this box here is my parameter space, and suppose that I have a point in parameter space that is at some likelihood value, L star, let's say. Then I can think of this point as lying on a hypersurface of constant likelihood. Okay, so all points on this surface here have the same likelihood. If I go inwards, I get points with higher likelihood. This is under the assumption that it really is true, that the likelihood peaks somewhere in the middle of my parameter box, right? Rather than peaking towards the edges. So if I go inward, I get a higher likelihood. Now, what is this famous prior mass? It is simple. I take the prior and I integrate over the volume inside here. That is the prior mass. So the prior mass is the integral inside this volume here of the prior, and that's it. And that I indicate by x, and so inside here I write x star. This is the prior mass associated with this hypersurface of constant likelihood. And then the integration element here is then called the element of prior mass, and that is just the prior times the parameter integration volume at some point. So first of all, one thing to note is the prior is normalized, so this prior mass takes on a value between 0 and 1. If you if you were to go to higher and higher likelihoods until you have just a point, then there's no volume left to integrate over, and that is when the prior mass is 0. If on the other hand I take a point on the boundary of my parameter space, that is where likelihoods will be the smallest. If I integrate over the entire parameter space, then I get 1, because again the prior has to be normalized. Okay. So now this is again the integral that I want to simplify, and like I said, I want to turn that into a one-dimensional integral. So I'm going to rewrite this as an integral over prior mass. So what I do is I take my prior mass element that's over there, and I write that as dx simply, and the likelihood here will then be a function of x. So what does that mean? Well, if I have a certain prior mass, then that will be associated with some hypersurface of constant likelihood, and that, whatever that likelihood is L of x. This is how I'm going to approximate my evidence integral. And then we'll see that as you go through an algorithm that will give you this integral, the posteriors for different prior masses you will get for free, but I'll get to that. So the idea behind nested sampling is to construct this likelihood function now not anymore in terms of points in parameter space, but in terms of prior mass. And we're going to do this by progressively finding locations in parameter space with higher and higher likelihood, and therefore smaller and smaller prior mass. Let me be more concrete. So I'm putting up this picture here, but really I'm going to use the board. So how does nested sampling work? So the way it works is as follows. So I'm again going to draw a huge box, which is my parameter space, and remember this is higher dimensional than the 2 dimensions that I'm drawing. But in any case, to begin with, I take n points that I sprinkle, or actually I don't just sprinkle, I draw them from the prior distribution. So I get n points, and in the example I'm going to give, I will make it 4 points. So I have a point here, and a point here, and a point here, let's say, and a point here, that I've drawn randomly from the prior distribution. For each of those, I can calculate the likelihood. I can always calculate the likelihood, right? The expression was there before. And so suppose this point has likelihood L0, and this point has likelihood L1, and this point has likelihood L2, and this point has likelihood L3. Then suppose that I've already ordered them in terms of increasing likelihood. So L0 is smaller than L1, is smaller than L2, is smaller than L3. Then if I first of all draw the surface of constant likelihood associated with this point here, then it will enclose all the others, because the others have a higher likelihood. They had better be inside this hypersurface here. And then similarly, there will be a hypersurface associated with L1. And there will be some hypersurface associated with L2. And finally, some hypersurface associated with L3, each being hypersurfaces of constant likelihood. So now I have, okay, so that is what I do. And then for each of those, for instance, if you have this point theta here that has likelihood L0, I can associate that to that also a prior mass, right? So I again take my hypersurface of constant likelihood, I integrate the prior inside that volume, and then I get a prior mass. So for instance, associated with L0, I also have some prior mass X0. Okay, so, and in fact you'll have this for all these points. In terms of X, you will have, this point here will have the highest prior mass because it encloses the largest volume. So my X0 will be here, and then the next one maybe will be here, and X2 will be here, and X3 will be here. So what am I going to do next? I want to move towards higher likelihoods because eventually I want to find the location where the peak of the likelihood occurs. So this point with lowest likelihood is going to do me no good, and I will get rid of it. So I'm going to cross this out. So also here, I'm going to put a big cross. I'm going to get rid of this point. But I'm not just going to get rid of it. I will record at least what it was. And so I get an X0 and an L0 value that I record somewhere. And now I can, since this is confusing, I'm going to erase the top here. I'm just going to put down a list of things, X0 and L0. So I'm throwing away this point from the pool of points, but I do want to keep n points, 4 points in this example. So I'm going to now choose some other point, which will have a likelihood associated to it, and so on and so forth. So let me choose another point, but I want that point to have a higher likelihood than the one I just threw away. Okay, so what do I do? I'm going to pick randomly from the prior again. Let's say I land here, some likelihood L prime. That's no good. It doesn't help because it has a lower likelihood than the point I just threw away. So I try again. And I end up maybe here the next time. Again, a lower likelihood than the point I just threw away. That's not good either. And then eventually, of course, hopefully, I'll end up, for instance, here. Let me call that L prime. And that's good, because that point here, clearly it's inside this hypersurface of constant likelihood, therefore it has a higher likelihood than the point I just threw away, and I keep it. Now, associated with that point, and now the plot is getting a little busy, but associated with that point is again some hypersurface of constant likelihood. And therefore, associated with it is again some prior mass, namely the integral of the prior inside that hypervolume. So, and now you can tell, well, it's hard to tell now from this busy picture, but it ends up between x2 and x3. So I'm going to have an x prime here, which is the prior mass associated with the new point that I just picked. Okay, so I've thrown away L naught here, but once again I have 4 points in the game because I chose a new one to add to. Now I'm going to go on. So now I just repeat what I just did. The next lowest point of lowest likelihood in the bin is this one, which has likelihood L1, and I'm going to throw that away. But again, I throw it away out of this pool of what are called live points, but I do record what it was and what its prior mass was. Okay? So I throw this away, and I choose again some point that will have a higher likelihood than L1 here. And I go on like this. So I keep going on until, well, there'll have to be some termination condition, of course, for this algorithm, which I'll tell you about later. Sorry. But, okay, that's good. So I keep going on, and now I have a list of x's and l's. Now remember, the quantity we want to compute is this likelihood integral, which we wanted to write as, well, likelihood essentially as a function of prior mass, integrated over prior mass. This I can approximate as a sum of likelihoods in this list here times delta xi, where delta xi is just the difference between successive prior masses. So basically this is going to be something like this, Li xi plus 1 minus xi. And if you want to do better, you can use a trapezoid rule and so on and so forth. But this is basically what you're going to do. And so in this way you get what will turn out, and we'll show this actually, what will turn out to be a fairly good approximation of the evidence. But now there's a big problem. Maybe you've noticed there's an elephant in the room. There is something that is something in this procedure that is so horrendously difficult in terms of computational power needed that in practice I cannot do it. You know what it is?
Calculating x for every point.
Exactly. That's not possible because you have to, or in practice not possible because you indeed have to identify this surface of constant likelihood that your point lies on, and that's a computational problem that is just as daunting as the problem that we set out to solve. So you can't do that. So you can't find these, or you can't calculate all of these x's in the list. So what can you do instead? Well, you can guess at what they are. And it has to be an educated guess. And an educated guess in statistics means that you draw from a distribution that you know the parameter has, in this case, the prior mass. So now I need to return to slides. So this is what I just explained. You throw away a point with lowest likelihood, but you find another one that has a higher likelihood, and you record these these prior masses, except that you can't, because you can't calculate them, so you have to statistically assign values for x1 in the first step, but then all of the other x's in the next steps. And so how do you do that? Again, it has to be an educated guess. Again, in statistics, that means that you draw from the distribution that you know the parameter or the quantity to have. Now, suppose that you consider the probability that the surface with the highest prior mass at some step in this algorithm, so this one in the first step, is at prior mass chi. Then you can write down the probability that none of the other samples in here have a prior mass greater than chi, right? And that probability is just a product of probabilities. What is this product here? It is the probability that the outermost, the x for the outermost point is no larger than chi, times the probability that the x for the next point is no longer than chi, and so on and so forth. So you get a product of these integrals here, and each of those are just, integrals up to some chi of a probability density distribution, which, however, is 1, because, well, this parameter x is uniform in itself, so there's a 1 here that I didn't write. In any case, you get a product of integrals, and these integrals are obviously trivial, they're just all of them equal to chi, so you get m copies of chi, where m again is the number of live points, as we call them, and so you get chi to the power m. That is the probability that your outermost surface has a prior mass equal to chi. But what you want is a probability density to pick from, but that's easy enough because you just take the derivative of this and that gives you the probability density. Because obviously a probability density integrated up to chi has to give me this probability. Okay, so I take the derivative and I'm done. Now, in practice, it is, and I'm watching the time here, in practice, it is convenient to talk not in terms of these x's, but in terms of what is called shrinkage ratio. It is really the same thing, it just turns out to be more convenient. So instead of all these x's, I can have what's called t. Now, t1 is defined as x1 divided by x0, so it's going to end up here somewhere, and then t2 is going to be x2 over x0, and I pick a t3, which is x3 over x0, and so on. And so, given an initial prior mass x1, what is the prior mass of the next outermost point going to be, having thrown away this? Well, I just take x1 to be t1 times x0, where this is the shrinkage ratio, and now I pick this number from its probability distribution. So that's equivalent to picking x itself from its probability distribution. Something is happening here. Okay, good. Now the shrinkage ratio has the same probability density. It is distributed in the same way as the x's themselves. Okay. So how do I determine these successive x's here? Well, I have to start from a certain x0, and I haven't told you what that x0 might be. But to get all the next ones, I keep multiplying by a shrinkage ratio, and all of those shrinkage ratios are picked from this distribution. Okay, and now I get a set of x's. And then I still have to choose an x0, and how am I going to do that? Well, normally what we do is not have 4 live points like in this example, but maybe 1,000 live points or 2 or 4 or 4,000 live points. So at the first sprinkling, at the very first step, when I pick points arbitrarily from the prior distribution, what the x interval looks like, so remember x goes between 0 and 1, but if you pick points randomly from the prior distribution, since the prior mass is uniformly distributed, what I'll get is something like this. Very densely packed, because in reality, again, I use very many live points. Not 4, but 1,000 or 2,000 and so on. And so x0 would be the prior mass associated with the outermost point here. Now, since these points are going to be uniform, there's going to be very, very many of them, and they'll be uniformly distributed between 0 and 1, well, x0 is going to be quite close to 1, probably. Why don't I just set it to 1, and I'm done? So, and then you have your algorithm complete. Okay, and so now, so this is what I say here. At the first step, just set x equal to 1. Then at the kth iteration, the life point with the largest prior mass will look like this. So what is this? It is k times, I have picked a shrinkage ratio, and I kept multiplying by shrinkage ratios, and x naught I've set to 1 here, so it has disappeared. So in the first step here, this is what you would have had, x1 equals t1 times x naught. Okay, in the next step, x2 is t2 times t1 times x naught, and so on and so forth, but x naught has been set to 1. So that is what I get. Now, remember that the distribution for shrinkage ratios looks like this. So it is then convenient to look at the log, the distribution of log of the shrinkage ratio, and that turns out to have a mean of -1 divided by m, and a standard deviation of 1 divided by m, where again m is the number of life points in the game. So that means immediately, or it's an easy exercise from this expression here, to see that log of x sub k has this mean and standard deviation. So at the kth step, the mean of log xk is k over m, and the standard deviation is square root k over m. So that means that the mean values of xk themselves go to 0 exponentially fast. That's the same as saying, yes, in my initial step, my points that I drew are almost uniform, or are uniformly distributed between 0 and 1. But as the algorithm progresses, very quickly, the picture will be more like this, where points are getting bunched together closer and closer to 0. And this happens exponentially fast in terms of number of steps. Okay, so eventually all of my life points will be, all of my life points will be bunched quite close to 0, which means that also I'm at the peak of my likelihood, because the volume inside of these hypersurfaces, constant likelihood, is shrinking exponentially fast. Okay, and then there's no obvious choice to end this sampling process. Let me, in the interest of time, skip this bit about this. This is a fancy way of ending the process. It is called the information integral, and then you can information is something that keeps increasing throughout the sampling process. Then you can say I'm going to terminate when my outermost prior mass is smaller than e to the power minus the information. Fancy way of doing things, but you can also do things in a simpler way. So as so remember, the evidence is this integral of likelihood, right? So basically, after some number of iterations, what you get is, if this is likelihood, and this is x, then you will have built up some part of the evidence integral already. But actually, it's handier if I bring this axis closer in, just handier to draw. Okay, so suppose I'm at this stage where this is so far the evidence that has been built up. Then I can estimate how much evidence there is still to go by saying, well, I know what my outermost x is, and I know what my highest likelihood of all of my life points is, which is typically a life point that is hereabouts. I suppose that its likelihood is here. Then this here is an estimate of the evidence still to be accumulated. A crude one, but it is an estimate. And so then you could say, for instance, well, when this box here becomes smaller than some small constant times the evidence already accumulated, then I stop. But where this alpha is then specified by the user. Then you can calculate what is the uncertainty on the evidence when you do this procedure. If your termination procedure involves this funny information thing, then it turns out that your uncertainty on the logarithm of the evidence goes like the square root of this information divided by the number of life points. And then for concreteness, for our purposes, with a few thousand life points, typically, and a clear signal, typically the uncertainty that ends up in the order of 10 to the minus 1, whereas a detectable signal has a log set, let's say, order of 100. So the uncertainties are quite manageable, certainly in our applications. And so, well, there's more details that in principle I could discuss, because I've pretended that I only have one data stream in all of these expressions involving D that I wrote down earlier. Well, this D, well, that would be the data from one detector then presumably, but there's more detectors. You have to take that into account, but it doesn't complicate things very much. And so that is how we arrived at these estimates for masses and spins for the various detections that have been made. And well, I see the plots that I put up here are now incomplete, of course, because there's a new detection. This was the first detection, very massive. This is mass 1, mass 2. This was the second detection. There's this LVT thingy here that we don't dare call a detection, but I think, well, most of us believe it's probably of astrophysical origin. And then finally there was GW170104, which was made public not long ago. Now, there's more that we will want to do in the future. We hope that it won't be only black holes that we're going to see from now on until the end of the advanced detector projects. We also want to see binary neutron stars at some point. And that's going to be extremely important, because the internal structure of neutron stars is extremely poorly understood. I think Niels Anderson, for instance, will be talking about that later. But anyway, there's a large uncertainty in what is called the equation of state of a neutron star. So that is determined by the interior structure. And for a physicist, the equation of state is just pressure as a function of density. But for astronomical purposes, you can view it as mass as a function. Mass as a function of radius of a neutron star. And you probably can't see this very well, but what the take-home message is that all these curves here are different, qualitatively different predictions by theoretical astrophysicists for what the equation of state of neutron stars should be, and you see that they vary enormously, okay? And these horizontal bars here are mass measurements from neutron stars in binaries, so they are constraints, if you will. A viable equation of state has to cross all three of those bars, but you see that many of them still do. So there's a huge uncertainty here. And we can help with this, because if you have a binary neutron star, then when it is at the point of merger almost, the two neutron stars will tidally deform each other. And how strong that tidal deformation is set by the equation of state. And also the tidal deformability of the two neutron stars, affects the curvature of space-time in their vicinity, therefore it affects the orbital motion, therefore it affects the gravitational wave signal. And so there will be some signature in the gravitational wave signal, which requires extra parameters to model. So instead of the 15 parameter dimensions that you have with just pure vacuum space-time, battery black holes, you will have extra parameters in the case of neutron stars to do with tidal deformability. And then something you could show, for instance, after a few tens of detections, you can already distinguish between a stiff equation of state, an intermediate equation of state, and a soft equation of state. But that does mean tens of binary neutron star detections. That is if you rely on the tidal effects alone. There will also be information, in fact lots of information in the merger itself, though it may be harder to extract at least the second generation detectors, because the merger of neutron stars is something that happens at high frequencies where we don't have good sensitivity. Then of course we want to see electromagnetic counterparts as well, so we want even more. Well, one point to note here is, so what if we had seen a binary neutron star coalescence as loud as the first detection, which was a binary black hole detection, of course, which is not expected to emit EM radiation, but the binary neutron star coalescence is expected to have an EM counterpart. Then, well, this is the sky error box you would have had with the two advanced LIGOs alone, but if you were to include advanced Virgo, then this huge error box, about 200 square degrees, can collapse to order 10 square degrees. Yeah.
Well, so you said you have to add some parameters if you're going to look at tidal effects and possibly extract more information from the merger itself.
Yeah.
But considering that we're going to be using gravitational waves to try and constrain a lot of these, presumably that's a huge open question with tons and tons of PE runs. So where do you start? Do you just go with the simplest model and then just work your way to more complicated until you find something else, or what do you do?
No, you can do one of two things. A very good question, by the way. So you can do one of two. You can do, first of all, model selection is the simplest thing. So you take all of these equations of state in this plot and then some, and you just rank them on, using model selection. You rank them on the basis of the data, and one of the models will come up on top. That doesn't mean that it will be the model that nature has chosen, but presumably it'll be close to it. So that's one thing you can do. The other thing you can do is, let's say you do a series expansion of the tidal deformability, which is denoted lambda. Just quickly, basically, if you have two objects, the tidal tensor from the one object will induce a quadrupole deformation in the other object, and the proportionality factor between the two is called the tidal deformability, which is set by the equation of state. So this function lambda of n is what you want to know. So one thing you can do is you say, I'm going to approximate lambda of n as a Taylor expansion. Taylor expansion, where the small parameter is the mass of the neutron star minus, well, some reference mass, which can be 1.4 solar masses, and you just go on like this. And you could stop at some order, because if you go to too high order, you'll get insensitive anyway. But the parameters you're going to be measuring are these expansion coefficients, which, if all neutron stars have only one equation of state, have to be the same for all of your events. And so you will get posterior density functions for lambda naught, and for lambda 1, and for lambda 2. And as you keep accumulating events, these will get sharper and sharper and sharper. And that is actually what is illustrated here in the case of lambda naught.
Are there any models that predict that different neutron stars will have different equations of state that would complicate this, or is that just totally crazy?
You see in plots sometimes a multi-valued equation of state, but then if you look at the values of the masses, they seem to be not very astrophysical. But I'm not an expert, you'll have to ask, for instance, Niels about that. Yes?
Talking about that image for and degrees of with advanced variable. Is it with the current state of advanced variable, or is it design sensitivity advanced variable?
This would have been design sensitivity, I believe.
Okay, so
no, wait a minute. No, I don't think so, actually. I think this was early advanced, but with an estimate, with something like 40 megaparsec BNS range. Yeah. Okay, so, well, I had a couple of more slides, but that morphs into the second lecture I'll have later, so let me stop here then for now. So in the first lecture I talked about how we measure things, essentially. So that is parameter estimation, and you can also do model selection. And that then has a number of applications. We have been able to measure reasonably accurately all sorts of parameters associated with the black holes that we saw so far. So the masses and the spins, which are of enormous interest to people, for instance, who work on how do binary black holes come about in the first place. Then we are awaiting binary neutron stars. I think we are not quite ready yet for various reasons to analyze those properly and extract all of the science that we can. But then there is also fundamental physics, and that's what I want to talk about now. So with the binary black holes that we've seen already, a lot has been done, and with further improvements in the detectors that we more or less know will happen, more can be extracted still. And so I'll be talking now about tests of general relativity with direct gravitational wave detection. Basically, the first detections of gravitational waves have given us access to the truly strong field dynamics of space-time, and before we didn't have that. Before there were the solar system tests. Well, actually, let me point to figures here. It's probably a bit hard to read, but here on the x-axis you have a characteristic mass of the system divided by its length, which is also a measure of the Newtonian potential. if you reinstate the appropriate factors of G and C. And then on the y-axis you have a measure of the strength of the space-time curvature, and basically the solar system is here, perihelion precession of Mercury for instance is here, the binary pulsar, which you will have heard of, is here, but our events are way up here. They are the most compact and the strongest space-time curvature by far of anything we've seen, and actually a better representation is the bottom plot here, where on the y-axis again you have a measure of the strength of space-time curvature, but on the x-axis now you have a characteristic time scale. It's basically a radiation reaction time scale, and the shorter the time scale, the more dynamical your system is, and of course the stronger the gravitational, the stronger the space-time curvature, well, the stronger the gravitational field is, and you see that our events are extremely dynamical because very short time scale, and again they're extremely strong in terms of space-time curvature, and moreover they are not dots. Again, the binary pulsar is here. They are not dots, they are streaks. They evolve through this plot as they were in the detector band, which again underscores the dynamical character. And what makes them even more cool is that they are pure, as far as we know, pure space-time events. As far as we know, at least for stellar mass black holes, whatever stray atoms would still have been around after that lengthy in-spiral process lasting millions of years. These things are excellent vacuum cleaners, but whatever stray atoms would still have been around at the time of the merger would have played no role in generating the gravitational wave signal that we saw. So this doesn't happen very often in physics, that only one field is involved in whatever process you're studying, and in this case it is just vacuum. It is only the curvature of space-time that plays a role. And so let me remind you, you'll have seen this before probably also, how does this go, the coalescence of binary neutron stars or binary black holes. So you start out with two objects that initially can be on very elliptical orbits, and they are in very wide orbits around each other, and then what gravitational waves do is, first of all, they take away energy from the system, so the orbits shrink, but the other thing they do is they take away orbital angular momentum, so the orbits circularize. And by the time the frequency is high enough for us to pick up the gravitational wave signal, at least with ground-based detectors, you can assume that the orbits have circularized, and then you have quasi-circular in-spiral, adiabatic in-spiral, until some last stable orbit is reached. Then the two objects plunge towards each other to form a highly excited black hole, and that then undergoes ring down as it settles eventually in a quiescent Kerr state. And then here is a cartoon picture of the waveform. So you have it during the in-spiral regime. You can see the tops of the waves getting closer and closer together. The frequency increases steadily. This regime is well described by the post-Newtonian techniques, where you essentially take physical quantities and make series expansions in power of V by C, where V is some characteristic velocity. That breaks down in late in-spiral. And input from numerical relativity is needed, and then finally, when the ring down regime is valid, you have black hole perturbation methods that are valid again. I remind you of this because in each of those three regimes, interesting physics is to be done. So that's hence the quick recap. And as probably Mark, for instance, will have explained, by now we know how to combine those techniques to produce in-spiral merger ring-down waveforms that are analytic or semi-analytic and sufficiently fast to generate on a computer that you can do data analysis with them. Now, the three events we've seen, this plot you may also have seen before, but let me go through it again then. So what you see here is the four events that we've seen so far. Three of those we call detections, and so they get the GW designation, and then you have the date in reverse order. This is the first detection, which was extremely loud and extremely massive. And the frequency of merger and the length of the waveform goes approximately like 1 upon the total mass. So you had a very short waveform in band. But if you look at the left-hand side here, here's frequency, and then here in blue and in red are the sensitivities of advanced LIGO around the time of, I believe, the first detection. The first detection here is seen moving through our sensitive frequency band. It has very little in-spiral, but the merger happened exactly at the frequencies where the detectors are the most sensitive. This bump here is the merger. Now, if you're interested in again, the truly strong field dynamics of general relativity, then this is the dream event for you. This is the golden event, and moreover, it is loud. Then the second detection here, the so-called Boxing Day event, was much lighter and therefore had much more inspiral in band. So if you're interested from a fundamental physics perspective in the way that near point particles in general relativity move around each other, and you want to check that in detail, then this is the event for you. And then came this event here, and it looks very much like the first one. That is because, again, it was very massive, but it was twice as quiet, and then we were at first kind of disappointed, maybe at least the people who are interested in testing GR, because what more could you extract from this event that you had not already learned from this one? Another reason it's twice as weak is that it is more or less twice as far away, and this helps then in studying another aspect of general relativity, which is how gravitational waves propagate over large distances. So nature was kind. Nature gave us the first three events, or the detections, are quite complementary to each other. Now, the talk is about testing GR, but there's a zoo of alternative theories out there, and how do we deal with that? Well, there is this thing called Lovelock's theorem. And what does Lovelock's theorem say? Well, suppose you list a number of assumptions that will seem reasonable. Then, given those assumptions, almost the only field equations for gravitation, the gravitational field that you can write down are the Einstein equations plus maybe a cosmological constant. And what are those assumptions? Space-time has 4 dimensions. Secondly, only the metric and up to second derivatives of the metric play a role. And that is, something we're accustomed to in physics. Usually, if evolution equations have derivatives up to second order. Then you want something in the field equations that is divergence free, which means that it means that you have field equations that are consistent with conservation of stress energy, and you want general covariance. If you want all of those things, then almost the only thing you can write down is the Einstein equations. But then you can drop those assumptions, and people want to drop those assumptions one by one or in batches. For instance, string theorists will want more than 4 spacetime dimensions. There's also the possibility of extra fields. There's ways to motivate that the gravitational field would be described not only by a metric, but also in addition a scalar field and maybe a vector field. And so then another assumption gets dropped, and so on and so forth. And if you drop these assumptions, then families of alternative theories of gravity open up. And how do you deal with that? Well, first of all, specific alternative theories can in principle be mapped to weirdness in this inspiral merger ring down process, or indeed in the propagation of gravitational waves. And people have, like Eunice and colleagues, have been working on this for a long time. But a problem with that, from our point of view, is that for none of those alternative theories, as far as I know, there exists an inspiral merger ring down waveform of the same quality as the ones we have for general relativity. And so, even though the leading order effect of some GR violation might be known for some specific alternative theory of gravity, leading order, for instance, in the post-Newtonian sense, that is a far cry from having full inspiral merger ring down waveforms. And so, what we do in practice, as much as possible, we try to perform model-independent tests. So what that means is you take your inspiral merger ring-down waveform that you have for GR, which is very faithful to, for instance, numerical relativity waveforms. It's been tested. We've tested the heck out of these things. We trust them. And then in selected strategic places in the structure of the waveform, you allow for deformations that are parameterized. So there's some extra coefficient coming in, and you can choose such coefficients such that they are 0 in the case of GR, and then you do the usual parameter estimation. You get a posterior density function, and you see whether the value of 0 is consistent with that. And that is what mainly we do. So let me first show the existing results from our 3 detections: 150914, 151226, 170104. So the simplest thing you can do to see whether your signal is consistent with general relativity is take your raw data, then go to your best fitting analytic or semi-analytic waveform, or the numerical relativity waveform corresponding to its parameters, and subtract it from the data and see what is left. And that is called residual data. And it had better be the case that residual data is consistent with ordinary detector noise, at least statistically consistent with ordinary detector noise. Now, although I won't go in detail, it is possible to associate a signal-to-noise ratio, squared here, associate that to these residual data and relate that to the signal-to-noise ratio that the detection itself had, and what comes in between is a fitting factor. So this fitting factor tells you how good of an approximation the signal that or the model that you've just subtracted, how good of an approximation that was to the signal that was actually in the data. And so you can just plug in the numbers. Let's say the SNR detection itself was about 25. It was determined that in the residuals there's at most a signal-to-noise ratio of 7, so this is an upper bound, which gives you a lower bound on this fitting factor of 0.94. So at most, GR violations are limited to 4%, you know this up front. That is at least for effects that cannot somehow be absorbed into a redefinition of the masses and the spins. So incidentally, since recently there's been a lot of hoopla about these residuals, and they allegedly contain some signals still and so on. Already in 2016 we published plots like this, where you have here a bound on the SNR in the residuals. This is what was measured, and this is a cumulative distribution function for what you get from randomly chosen chunks of data that probably don't contain anything, and you see that that what we find is quite typical. So that is one thing, but we want to go on. Especially the people who spent their life essentially developing the post-Newtonian formalism, for example, want to know, well, how accurately can you measure those parameters, and is there any GR deviation to be seen? And so what we do is we take a bunch of, I wonder if I have a better slide, or did I ditch it? Unfortunately, I ditched it. Yeah, okay. Well, we'll have to make do with this one. So basically, Mark, for instance, will have talked about these phenomenological waveforms that he helped develop. And these are waveform models where you have an in-spiral regime, and then what we call an intermediate regime, which is the end of in-spiral, where these post-Newtonian methods are no longer valid because there's no quasi-circular in-spiral anymore, and then the merger ring-down regime. And in each of those, there are a set of parameters that determine the frequency evolution, and so those parameters, in those parameters, you can essentially allow for a deviation. So let's say, where should I write this? Let's say P sub I is one of those parameters. This could be a post-Newtonian coefficient. It could also be some coefficient to do with the merger ring-down behavior, whose value really comes from fitting to numerical relativity waveforms. But you replace this by P sub I times 1 plus some relative deviation. And this number here will be 0 in general relativity, right? Now what you do is, you do the usual parameter estimation, but instead of 15 free parameters, you now have 16 free parameters, because on top of all of the others, this delta Pi is free. And then you can calculate probability distributions, and it had better be the case that the value of 0 is consistent with your distribution, otherwise GR is violated. And that is how you should read these plots. So basically, so each panel, or each of those blobs corresponds to one of those testing parameters delta P hat here, and the blobs themselves are the shapes of the probability distributions. So you do this for in-spiral. These are then just possible deviations in the post-Newtonian coefficients. But like I said, there is this late in-spiral regime where idiopaticity is no longer valid, and there you have relative deviations in parameters that come from numerical relativity, really. And then finally, there is the merger ring-down regime, where again you have a bunch of parameters to be estimated. Now, in the case of the first detection, GW150914, it had a short in-spiral, but the merger was, like I said, almost exactly at the frequency where the detectors were the most sensitive. So that is where you then expect to get the most information, and not so much from the in-spiral regime. By contrast, the second detection had an extremely long in-spiral in band, and the merger was at such high frequencies that you lose resolution there. So there you can expect the in-spiral coefficients, basically, like I said, post-Newtonian coefficients, to be better constrained, and this is what we see. Whereas the merger ring down, happening at very high frequencies, there things go to hell. You can't tell anything from this event, and that is as expected actually. And then you can combine information from multiple sources just by multiplying these posterior density functions. You can actually prove that this is the correct thing to do. You have to put some power of the posterior in front, but other than that, combining information from multiple sources comes down to multiplying posterior density functions. And this is the combined result you get then from GW150914 and GW151226. And that is now, in terms of this kind of test, the state of the art, because, like I said, the third detection, 170104, was much like the first one, but twice as weak. And so for this kind of test, you gain nothing. This is the combined result from the 3 detections, and you can hardly tell any difference from the combined result from the first 2 detections. That also is as expected. And then I hasten to add that in this combined result, and also in the individual ones, of course, the value of 0, the GR value of 0, is consistent with all of these posterior density functions. Okay. Yeah.
Is there a sort of physically understandable reason why things like the 2pn term in the in-spiral is much less well constrained than the 1.5pn or the 2.5?
Yes, there is. So suppose that when you combine information, the handy thing to have is relative deviations. It turns out that is the handiest thing to, and then you can just multiply your posterior density functions. Suppose that instead I would have plotted PDFs for the absolute deviations, then you would have seen a progression from low post-Newtonian order to high post-Newtonian order. You'd have seen progressively the posterior densities getting wider. But so why is it that the relative ones fluctuate somewhat? That is because the values of the parameters themselves, well, they change from one post-Newtonian order to the next. And you're essentially dividing the absolute deviation, which shows a monotonic trend. You're dividing those by the values of the parameters themselves.
Excuse me?
Yeah.
For the first detection, you say, right, the in-spiral is technically not good enough to really do it.
Mm-hmm.
But you did it, and there is like a few cases where the 0 is not in the 90% interval, right?
No, it is. It is in all cases. Maybe you can't see it very well.
Okay.
There are offsets, but never more than something like 2 sigma.
Okay.
Yeah.
So it's just...
Yeah. So now this is, and then you can focus on the post-Newtonian description of the in-spiral, because that is what we have the most analytic control over, and that is therefore what the theorists are going to be the most interested in. This is actually just a recasting of what I showed earlier. So these first boxes here of the post-Newtonian coefficients, you can translate that in a bound. How at 90% confidence interval, how large can these delta p hats be for all the post-Newtonian orders? And probably somebody told you about the half post-Newtonian orders. This is a historical accident. So 0pn, of course, is the leading order. Half pn means 1 power of v by c beyond leading order. 1pn is 2 powers of v by c beyond leading order, and you go out from that. Now, first of all, in this plot, the inverted blue triangles are bounds you could obtain from the binary pulsar. So that's the binary neutron star system that can be observed by means of radio astronomy and has been for many years. And the orange boxes are the bounds we got just from the first detection, despite it having 5 to 7 in-spiral cycles in band only, depending on how you count. Now, at the leading order, the binary pulsar people beat us by an order of magnitude, and that is because they have been observing their system for years now, whereas our signal was in band for 0.2 seconds or so. And so that is how they gain. However, the only thing they have access to is the shrinking of the orbit, and that shrinking, it turns out, is very well described by the quadrupole formula, which is the 0pn approximation of the orbital motion in GR. But if the quadrupole formula is a very good description of what you see, that means you're not probing any of the richness that goes beyond the quadrupole formula. We, however, because of there being so much structure in the signal, we were able to place bounds up to fairly high post-Newtonian order in a fairly stable way. And that was just, again, with what in the order of 5 inspiral cycles. So that was a rather nice result. Then, what are the physical meanings of some of these coefficients? Well, if the graviton had a mass, and I'll return to that, then it would first show up at first post-Newtonian order. Then the 1.5 post-Newtonian order is extremely interesting because it is the lowest order at which dynamical self-interaction of the gravitational field kicks in. It is also the lowest order at which spin-orbit interactions kick in. Now, I should have cited here alongside a paper from the early 90s by Luc Blanchet and Satya. Luc Blanchet is one of the developers of the post-Newtonian formalism, where they already pointed out the supreme importance of this coefficient for these reasons, and also pointed out that LIGO would be able to measure it very well. This is the level of measurement we were at with one event, but I haven't folded in the Boxing Day event yet, so bear with me. And then you can go on at second PN order spin interactions come in for the first time, or if you're interested in alternative theories of gravity, gravitational parity violation would come in at 2 PN at lowest order, and so on. This is the combined bounds from 150914 and 151226. I'm not showing anything that includes 170104 because you gain nothing because of it being very similar to the first event but weaker. And you see that the 1.5 PN coefficient is already determined down to 10% or so, which is already a fantastic result. Luc Blanchet is very happy. But then, as we see more and more of these binary black holes, the expectation is that roughly this bound will go down with the square root of the number of detections. So it's a good guess that by the end of this decade, we will have pinned down the 1.5 PN coefficient down to the few percent level. So that is what happens at the source, or the inspiral merger ring down behavior and whether it's consistent with GR. But then these gravitational waves propagate over large distances, and that allows you to say something about possible anomalous dispersion going on, maybe because of the presence of a graviton mass. Now, what we saw, of course, was not gravitons. We saw a classical gravitational wave, but nevertheless, if you take the Lagrangian of general relativity and you introduce a mass term, then this will also have an effect on classical waves. And in particular, what happens is that the high-frequency components of the wave will travel slightly faster than the low-frequency components, and both will travel slower than the speed of light. And so you get a sort of compression of the waveform. So this is the anomalous dispersion relation you would get. So in general relativity, in the right-hand side, only the first term is present. Here's the massive graviton term. Since we are talking about waves, you can introduce a Compton wavelength, of course. And this here tells you how the phase in the frequency domain changes because of the presence of this massive graviton, or because of this Compton wavelength. You see it goes like 1 upon Compton wavelength squared, and it is directly proportional to the distance traveled. This is a cumulative effect, right? This accumulates over the large distances traveled, and for that reason, it is also extremely well measurable. You can dig very deep and put a very sharp bound. In particular, we were able to put a lower bound on the Compton wavelength of the graviton of 10 to the 13 kilometers, it's about a light year, and an upper bound on the graviton mass of 10 to the minus 22 electron volts. Essentially, that is, 4 orders of magnitude better than the current best bound on the mass of the photon. So if you know anyone who is trying to measure possible mass of the photon, send them our way. We know how to do this. But then you can go further. You can say, well, if I'm going to modify my dispersion relation, then I might as well go for possible different terms that appear here. And so, for instance, a simple thing that you can do, which is motivated by specific alternative theories, although it is a model-independent test, is put here momentum to some power alpha, and then the capital A here gives you the size of what will become a Lorentz invariance violation. That is what these terms do. Except for the term alpha equals 0. In the case alpha equals 0, if you identify A with the square of the graviton mass, then you're in the previous case. But for A greater than 0, this is a Lorentz invariance violating term. And in particular, it modifies the group velocity of gravitational waves like so. So in the left-hand side, you have V over C. So in GR, that would just be 1. But with this extra term in the dispersion relation, you get an extra term in the group velocity that looks like this. Now, depending on the sign of this capital A and the value of alpha, this term can be positive or negative. For instance, if alpha is greater than 1 and capital A is positive, then this will be greater than, this will be positive, and therefore you have superluminal propagation of gravitational waves. If, on the other hand, this second term is negative, it's subluminal propagation of gravitational waves, and in either case you also have anomalous dispersion. And then you can calculate, these are complicated expressions, doesn't matter, but you can calculate to leading order in capital A, the violation of Lorentz invariance. To leading order in A, you can calculate what kind of effect that has on the gravitational wave phase, and that is what is depicted here.
What would superluminal speeds of gravitational waves mean in regards to, like subluminal would mean massive graviton. Would superluminal mean anything in terms of the graviton?
Not necessarily. So even subluminal doesn't necessarily mean that there's a massive graviton. It could be a Lorentz invariance violation with a zero graviton mass. So that is, for instance, if you take the case alpha, let alpha be greater than 1, but put a negative A here, then this term here will be negative, therefore the group velocity will be slower than the speed of light, and yet you're not in the massive graviton case. And then superluminal means that the speed of gravity is faster than the speed of light. There's no immediate relationship between the two. So what we're going to do now is, for fixed values of alpha, we're going to let this A vary, again, along with all of the 15 other parameters in the problem, the masses, the spins, and the distance, and the sky position, and the what have yous. In addition, so we have this capital A, so now we're measuring 16 parameters at once. And these are the bounds you get on A, the upper bounds on A. There's two kinds of markers here in this plot corresponding to a positive value of A or a negative value of A, and then whether a marker is filled at the top or at the bottom denotes superluminal or subluminal propagation. And so you see that we, like I said, we put bounds for different fixed values of A, and these bounds are fantastic, right? So first of all, the scale here is pico electron volts to some power, and you get down to 10 to the minus 20 here. Fantastic accuracy. Now, being physicists, we want to express things in terms of some characteristic energy scale or some characteristic length scale. And you can do that. So you can define a length scale based on this capital A here, like so, which the definition will be different for every value of alpha. But nevertheless, for every value of alpha, you have some characteristic scale. And for A greater than 0 or smaller than 0, and different values of alpha, these are the lower bounds we got on that length scale. And look at this number here, 10 to the 41 kilometers is not only many orders of magnitude larger than the distance traveled by the wave, it is orders of magnitude larger than the Hubble length. So now you might say, well, how is it possible that you can put bounds like this? And the reason is that, especially for the higher order alphas, the way these characteristic length scales enter into the dephasing is very nonlinear. So in a sense, the accuracy or the kind of bounds you can place also depend very nonlinearly on the value of lambda itself. So, and you know, these are extremely high precision measurements that in physics you will see in many places, like in particle physics and so on, but this is the first time I think we see them in gravitational waves. So now we return to the source. There are further tests of general relativity that have been done. For instance, you can look for, this is something Mark already explained I think, but you can look for consistency between the in-spiral part and the post-in-spiral part. So you cut your signal in half. First you analyze the first part, and you get basically the masses and spins of the component objects during the in-spiral. And the final part, the second part of the waveform, will give you the mass and spin of the final remnant object. Now, numerical relativity, or actually general relativity, predicts that, of course, there will be a relationship between those two. If you know the masses and the spins of the initial objects, you should be able to figure out from general relativity the mass and the spin of the final remnant object. Now, this cannot be done analytically on a piece of paper, but from numerical relativity, you can make accurate fits. And this was done by these people. Actually, more accurate fits are available now, but those are the ones we used. And so you can test the relationship between masses and spins of the initial objects, mass and spin of the remnant object. And so I'll be brief here because I think Mark already showed this. So here's final mass and final spin, and this is a 90% probability contour coming from the in spiral, and this from the post-in spiral, and you see that they have a region of overlap. The dark 90% contour comes from the in-spiral merger ring-down waveforms inferred from those, and it's not part of the test, but it is of course gratifying that it lies smack in the middle of this region of overlap. Then ring-down. Ring-down is even for the first detection, where the ring-down was reasonably in the sensitivity, in the most sensitive band of the detector, even there, and with its loudness, the event was not loud enough to extract much information about the ring down. But let me just say that in the ring down regime, what you do is you take a Kerr metric and put linear perturbations on them and linearize the Einstein equations around that Kerr metric. And what you'll find then is that the ring down signal is a superposition of so-called quasi-normal modes, which is a complicated way of saying is superposition of damped sinusoids. And each of those sinusoids has some characteristic frequency and a characteristic damping time. Now, in general relativity, it is not the case that immediately after merger, this linearized regime is already valid. Immediately after merger, you have a strongly deformed object, you are still in the truly strong regime of GR. So when does that linearized regime kick in? Well, about 10 m after the merger. So remember, in general relativity, playing with C's and G's, masses can be turned into a time or a length scale if you want. And so 10 m is a time. And for the first detection in 150914, 10 m corresponds to about 3.5 milliseconds. Now, we didn't expect, we tried, but couldn't find evidence of more than one quasi-normal mode. This is kind of as expected. There will be some least damped quasi-normal mode that dominates. And so what this picture refers to is a situation where you take a single damped sinusoid and you try to fit it to the tail of the signal. Now you have to decide on a start time. When do I start fitting? This is frequency, by the way, and this is decay time. This is again the 90% probability contour inferred from the in-spiral merger ring-down waveforms. And then the dashed contours come from fitting a single damped sinusoid, but starting at different times after the merger. For instance, this one. Suppose you start only 1 millisecond after the merger. We know from numerical relativity that the linearized regime, this description in terms of damped sinusoid, is not valid at all. And indeed, we see that the result is incompatible with what is inferred from the full in-spiral merger ring-down signal. So, not unexpectedly. But now suppose you fit 3 milliseconds after the merger, which is already closer to the 3.5 millisecond prescription. This is the 90% contour that you get, and it is already consistent with what is inferred from the full in-spiral merger ring-down waveform. And then you could start fitting even later. For instance, 5 milliseconds is this contour, and again it is consistent, but the later you fit, the bigger this contour becomes, of course, because you're using less and less of the signal and you're losing measurement accuracy. This is as expected. And this is what we got from the first detection. We're not done yet, and I'll come back to that later. We want to do this better. Into the future. So first of all, assuming GR is correct, I showed you those what we call violin plots, these plots with many panels and blobs that are the probability density functions for these relative deviations from GR. Assuming GR is correct, the bounds on those violations are going to get tighter and tighter, like I said, roughly with the square root of the number of sources, and eventually they'll be so peaked that you'll say, okay, GR is correct. Except that it can happen that if there is a GR violation, it can happen that if this is one of those delta PIs there, that one event will give a GR violation in one direction, and the next event gives one in a different direction, and then the other way around again. And if you keep multiplying these probability densities, you'll get this. And apparently, you have consistency with GR, whereas there is actually a GR violation. A better way, which we have already developed and is more or less ready to use, but you can also look for GR violations by model selection. So So what you do is you define a model, mod-GR it's called here, and you compare it with a GR model and you compute an odds ratio like I explained earlier. And so a mod-GR model might mean that you let you allow for a relative deviation in the 1.5 post-Newtonian coefficient and see what you get. And so here's a plot where the log odds ratio is shown. In the case of GR, you have the blue, and the red here is for a 10% violation at 1.5 pn. For a single event, you can already tell something is going on. Incidentally, for a single event, you only get one log odds ratio, a single number. So these distributions are simply the results of many, many simulations of what you get from a single event. But you can combine information from multiple events. I didn't explain in detail how to do that, but you can do that also with model selection. And then even when something like this alternating behavior would be happening, nevertheless, evidence against GR being correct will build up. So model selection will then eventually tell you, yes, there is a very clear GR violation, like this picture suggests here. And then we can, go nuts in a sense. So far we've been looking at the in-spiral merger ring-down dynamics, right? So the dynamics of space-time almost as a whole in such a process. But how do we know that the objects involved were really black holes? Can we not go into more detail and see and actually think about alternatives for black holes? That is the job of the theorists. And then how would we measure deviations from the black holeness of the compact objects? And there's a whole bunch of so-called black hole mimickers in the literature. So these are objects that can have masses in the black hole range and can even be so compact that a light ring sticks out, but they're not black holes. So boson stars are an example where you have a blob of scalar field that is basically a star made out of a scalar field. If dark matter is composed of particles and they are fermions, then you can imagine star-like objects forming that are held up by degeneracy pressure, and those are dark matter stars. And then there are gravis stars. A gravis star you can imagine to be a blob of dark energy in this case, so a region of space-time with a positive cosmological constant that tries to expand, but it's held together by a crust of normal matter. How such objects would come into being, nobody knows, by the way. So this is the most speculative of the bunch by far. And then from string theory come alternatives to black hole horizons inspired by anyway, so you have things like fireballs and fuzzballs. I won't go into detail, but essentially in those scenarios there is no black hole horizon. There is just a thin region where the stress energy of basically space-time itself is extremely high, except it is still permeable. So you can go both ways. It's not a real horizon. How would you find those things? This is the summary of what is to come. First of all, you could find them by looking for tidal effects during the in-spiral. If it is really two black holes that you have spiraling towards each other, they will deform each other, but only when they're extremely close together. Then deformation shows up and not before. So tidal effects should be essentially invisible for black holes, but not, for instance, for boson stars or dark matter stars. Or, I already mentioned ring down, you can look for some anomaly in the ring down spectrum. So are the frequencies and the damping times of the quasi-normal modes really as predicted by general relativity? And then finally, there is this idea of gravitational wave echoes continuing after ring down, and I'll get back to that. Yeah.
For the dark matter stars, is that dark matter that somehow started fusing? Like what?
You have to imagine, so suppose dark matter, first of all, is composed of fermions, then you can imagine a cloud of them forming a star, and the star is held up simply by degeneracy pressure, the fact that two fermions don't want to be in the same state. So first of all, the anomalous tidal effects. And here's a cartoon picture. So there's meant to be a binary here. The other object is in this direction, but it's not shown. But the other object will have a certain tidal tensor and will exert tidal forces on the first object. And that will, to leading order, induce a quadrupole deformation in this object here. And that quadrupole deformation is denoted Qij here. And Eij is the tidal tensor that is inducing that quadrupole moment. And again, to leading order, those two are related, by this lambda here, which is called the tidal deformability, and this tidal deformability depends on the mass of the object here, but also on its internal structure or the equation of state. Now, in the case of black holes, to the approximation shown, black holes will have lambda identically equal to 0. In the case of boson stars and dark matter stars, lambda will be positive and some function of mass, right? And for gravastars, lambda is negative. Now, those tidal effects, they enter the inspiral phase. So what happens is the two objects get close together, they start tidally deforming each other, therefore the curvature of space-time in their vicinity changes, therefore the orbital motion changes, therefore the gravitational wave emission changes. But these effects enter the inspiral phase at a very high post-Newtonian order, namely 5 order. So that's order v by c to the power 10 beyond leading order. Then you might say, well, is there any hope of seeing anything in that way? But the saving grace is that they enter at 5 order through this combination here. So this is the radius of the object divided by the mass of the object all to the 5th power. And some g's and c's should be reinstated to make this dimensionless. But already for neutron stars, this quantity here is order 10 to the 2 up to possibly 10 to the 5. So yes, you're very high order in V by C, but the prefactor in front is not order 1. It can be huge. And that is how you can hope to see these effects. Also for neutron stars, like I mentioned before, you can infer or at least constrain the equation state of neutron stars in this way. However, you can also look for tidal signatures in, for instance, dark matter stars or boson stars or indeed gravastars. And since these objects are allowed to be less compact than neutron stars, you can expect an even larger effect. Basically, this is 1 upon the compactness, right? Mass divided by radius is how compact the object is. But this is 1 upon the compactness to the 5th power. So less compact means that very rapidly the tidal effects become large. Then there is testing the no-hair theorem, which means that I'm now returning to the ring down. So I mentioned that with GW 150914, the ring down was kind of a weak part of the signal, had a signal-to-noise ratio of not even 8, I think. Now, it's worth remembering that advanced LIGO currently is still a factor of 3 away from the final intended design sensitivity. So if you would see an object like this in a LIGO at design sensitivity, it would be 3 times louder, and you would have an SNR of, well, above 20 here. And this will, in the near future, allow for indirect tests of the so-called no-hair theorem. So what is the no-hair theorem? It says that if you have a stationary black hole, then that black hole is determined by only 2 numbers, namely its mass and its spin. If you have those 2, you have the whole geometry of the black hole. Essentially, electric charge is in principle also allowed, but probably that won't occur for astrophysical black holes. That translates itself into that linearized general relativity that you do around the Kerr background to get to these quasi-normal modes. That translates into the fact that these characteristic frequencies and characteristic damping times can only be dependent on the mass of the spin and in a very particular way, which GR predicts. It's a formula. And again, you could put bounds on deviations from these relationships. So you do exactly what I did here. Instead of P sub I, you have the omegas as function of M and J, or the taus as a function of M and J, and you allow for a relative deviation. And you see that these relative deviations with an object 3 times louder, a detector 3 times better, that these relative deviations can actually be measured. And then again, you can combine information from multiple sources, just multiply the posterior densities together, and eventually you get these extremely tight distributions. And then come echoes. This is rather speculative, but also kind of interesting. So I mentioned that, for instance, in string theory, you have these ideas that maybe there is no horizon. There is something that has a strong stress-energy tensor, but it's permeable. You can go both ways. Now, when a black hole gets formed as the result of a merger of 2 black holes, if it is a standard GR black hole, then, well, part of the radiation will go outward towards infinity, and that is what we can measure. But part of the gravitational waves fall in, never to be seen again. But with these objects, what happens is that the ingoing part of the gravitational waves can bounce around in these what are called effective potentials. So basically you have a gravitational wave bouncing in the interior of an object, and each time the wave gets to the outside and reflects, part of it leaks through. It's just like in quantum mechanics where you have a wave function, it hits some boundary, some potential boundary, but some of the wave function leaks through. Something very similar, this is just classical physics, but something very similar happens. And what happens then is that you get bursts of radiation coming out at fixed time intervals, delta t. And what is delta t set by? Well, there's this little n here as a prefactor. N depends on the nature of the object. So for instance, in the case of a wormhole, n is equal to 8. And in the case of gravastars, I think n equals 4. And boson stars, n equals something else. But it's something you can calculate. Then m is the mass of the remnant object. And then this L here is the characteristic size of whatever is replacing the horizon. Now let's plug in some numbers. So let the mass m be the one from GW 150914's remnant object, and let L be the Planck length. So if it is some quantum gravity modification that causes the absence of horizon, then you can imagine that the thickness of whatever replaces the horizon is the Planck length. So I plug in the Planck length. So what I get then for delta t is order 100 milliseconds. That's already good news if you want to find these things, because the answer could have been a million years. Or it could have been less than a millisecond, and then it would have been confused with part of the ring-down signal itself. Instead, it is well separated also from the ring-down signal. And preliminary calculations suggest that the amplitudes in the first few echoes might be visible with advanced LIGO already at design sensitivity. And incidentally, I think, yes?
I was talking to Niels Anderson about this, and he said that for this to occur, that the black hole itself can't be spinning, but we know black holes do spin, so...
No, in these simulations, yeah, it's true that non-spinning objects were assumed, but it is reasonable to expect that since the same behavior is seen in objects of a very different nature, so wormholes or boson stars or gravastars, the next step for the theorists will be to set them spinning, of course, but you can already guess that the qualitative behavior will be similar, probably. Incidentally, Alicia was talking about the fact that the stretches of data that the detections are in, they're already public. Anyone can access them, download them, do data analysis on them. And there's actually already a claim in the literature by people outside the collaboration that they had detected echoes, or in fairness, they themselves said detected with 2.9 sigma, which is not something that wins you a Nobel Prize, but nevertheless, that would have been significant. However, people from the collaboration have looked at this, and it turned out that their background calculation was insufficiently extensive, and basically their 2.9 sigma had rather a large effective error bar on it. And if you do have a more extensive background calculation, then significance drops well below 2 sigma. But in future, you can look for this. Another thing, by the way, that these people assumed was a very specific shape of the echoes that, even for the kind of object they were assuming, is probably not correct. And so what we will be doing in the future is use these model-independent methods of searching for things to analyze this. Then you can look for alternative polarization states. So as I'm sure you know, in general relativity, there's only the plus and the cross polarization that are depicted here. But actually, in metric theories of gravity, you can have up to 6 different polarizations. You can have 2 scalar polarizations. This is called the breathing mode. Basically, instead of space-time stretching in one direction, compressing in the other, and then the other way around again, it stretches equally in the x and y directions, if this is the direction of propagation. You can have also this kind of behavior in the direction of propagation, like shown here, and then you have the 2 so-called vector modes. Now, for GW 150914, what we did was something fairly extreme. So we already knew that with a network of 2 detectors, you cannot tell the difference between the polarization states of pure general relativity and any of the alternative polarization states. You need a larger network for that. But what we did was do, again, model selection on 2 rather extreme models. Well, one is simply the GR model, actually. And the other model, however, assumes that all of the power of the signal was in a scalar mode, and there was 0 power in plus or cross polarizations. Of course, even if GR is violated, there's nobody who would expect that to happen. But we wanted to make a point here, namely, if you compute, well, actually the log base factor between those 2 hypotheses, you get something that is consistent with 0. So that means the base factor itself is consistent with 1, that is, you cannot tell the difference. And that is, again, as expected. You need to probe alternative polarizations, you need a network of detectors. And then you can also use actually continuous wave signals from pulsars to look for alternative polarization. So these people here showed that if you were to have vector modes coming from the Crab pulsar in this case, then if you have a model that allows for all 6 of the polarizations, then you will pick up a signal at a lower strain than if you assume just the GR polarizations. Yes.
So the stochastic signals, I've heard that they're more, like the stochastic group is more sensitive to some of these other polarizations than the original polarizations, than the GR predicted polarization.
Yeah.
So why is that not also true for compact binary mergers?
Well, actually, this is a result from the stochastic group, and they are assuming a background of BBHs. So basically, what probably once every 15 minutes, you know this of course, but the gravitational wave signal from a binary black hole comes by, but most of them will be too weak to be picked out individually. However, they will show up as a kind of correlated noise in 2 detectors, and you can pick that out. And then you can look for, this is what is actually done here, you can look for, again, alternative polarization states. And so these guys did a simulation here, assuming scalar polarizations again, versus polarizations from GR, and here you have, for different signal-to-noise ratios of this signal, of this stochastic signal, you see how well log odds ratios for a violation of GR are separated from 0.
So it's just more that they have like way more signals to compare.
Yeah, if you have only one extremely weak signal, we know that CW signals are going to be weak, even if you integrate for a long time. We know, on the other hand, almost certainly we will, in a couple of years' time, see the background, the stochastic background of the superposition of BBH signals. So if you already know you're going to see it, then yes, of course, you will be able to make stronger statements. And then this is the far future, and I'm almost done. Can't believe I'm keeping it on time. But so Einstein Telescope, or in the US Cosmic Explorer, is a third generation ground-based instruments that people are looking into. For instance, Einstein Telescope would be a triangle of, it's underground, it's 10 by 10 by 10 kilometers, triangle shape fitting up to 6 interferometers that are V-shaped, so that they do fit in a triangle. Already in 2011, a conceptual design study was published for Einstein Telescope, and basically what they did is they asked a bunch of clever instrumentalists if you had €1 billion to spend and given 20 years for foreseeable developments in better mirror coatings, better mirror suspensions, and so on, what do you think is possible, and what should you build? And what they came up with was this kind of design. Here you will observe probably in the order of 100,000 binary coalescences per year, which means you can combine information from all of these sources to get bounds on, for instance, the post-Newtonian coefficients at a fraction of a %, not just for the 1.5 PN coefficient, but for all of them. So that's one thing you could do. You would, if black hole mimickers exist, you would not only observe them or be able to tell from the tidal effects, you would actually be measuring their equation of state. And then there's also the space-based detectors, LISA, of course. Both in Einstein Telescope and in LISA, you can hope to see events where one of the black holes is much more massive than the other one. In the case of Einstein Telescope, that would mean one black hole has 1,000 solar masses, and the other one is a stellar mass black hole, or maybe even a neutron star. In the case of LISA, it would be one object has 1 million to 1 billion solar masses, and the other, again, is a stellar mass black hole or a neutron star. Now, when such a small object is captured by a heavy black hole, then basically you know, it will have no time to circularize. And so what you have is not quasi-circular in-spiral. Instead, you have a very complicated orbit, these MD orbits that people were talking about before, with extreme periastron precession, with extreme precession of the orbital plane, and the zoom world behavior, and so on and so forth. Extremely complicated objects. And again, if you're interested in the description of just the dynamics of objects in general relativity, then that is kind of the signal that should be your dream to see. So that will probably be seen. And then there's the interesting possibility of observing binary black holes both in the LISA band and in the Einstein telescope band. So when the two black holes are still far apart, so that the gravitational wave frequency is low, you would see them in the LISA band, and then some months or even years later, they would enter the band of ground-based detectors, and you would be able to compare the low and high frequency content. And so, yeah, I think the future is bright. I will just leave you with this summary here.